Okay, the tool that we'll be using to acquire data to measure the speed of sound is some freeware, and the freeware controls your computer sound card, and there's lots of functions. It's got lots of functionality, and it's called Soundcard Scope. It was written by a German electrical engineer. I believe his name's Mr Zeitnitz. So I'll open that up and let you see what it looks like. Okay, so here it is. And continue. Okay, there you go. Now, right here, what we're looking at, as I speak, the microphone is picking up my voice and transforming those pressure waves into voltages. And this is in the time domain. The y-axis, up and down, is the amplitude. That's the strength of the signal, the loudness. And this is the time axis, time. So if I whistle with a constant tone, I'm not a good whistler, but you'll see more of something that looks like a sine wave. That's a constant tone. You see the constant, nice, evenly modulated sine wave. Now let's look in the frequency domain. This is a spectrum analyzer. I'm going to change this upper limit to about 4,000. Okay, now if I whistle, you see a peak right around, what, 2,200 hertz, 2,200 hertz roughly. And what that means, okay, so this is in the frequency domain. Now the y-axis is still amplitude, but this axis is frequency. The x-axis is frequency. So it picks up the frequency, the dominant frequency in the sound. Notice that when I'm talking, there's a collection of frequencies, a superposition of all kinds of frequencies, all kinds of tones. You can see that peak move when I try to change the tone of my whistle. So that's a spectrum analyzer. Now what we're going to do is we're going to use the time domain to measure the speed of sound. And I'll talk more about how we're going to do that in a minute. Also, this piece of software, you can generate tones. For instance, mosquitoes, they flap their wings. I believe around 400 hertz is the dominant. They flap their wings at a particular frequency, flaps per second. That would be 400 flaps per second, 400 hertz. And this is what a mosquito next to your ear sounds like. So can you all hear that? And then if you look at the frequency, well, you really can't see it because it's down here in the noise level at low frequencies. But anyway, that's what a mosquito kind of sounds like. But if we change the frequency to, say, right where my whistle was, let's see if we can pick that up with the scope here. That doesn't pick it up too well. I need to have a microphone for that. But anyway, we'll just stop there. Okay, so anyway, you can generate all kinds of tones. For example, you can sweep the frequency. You could start at 1,000 hertz and end at, say, 10,000 hertz. So you start at 1,000 hertz and end at 10,000 hertz. So this is a lower tone. This is a really high tone. It's really annoying. And let's do a 10-second sweep. So I'm going to put the sweep on. Let's let you hear that. Okay, so you can kind of see when we were looking at the spectrum analyzer, you could see that peak, even though it's buried in noise, move across the screen from when we started at 1,000 hertz here all the way to 10,000 hertz. So what we're going to do, once again, we're going to use what's called the oscilloscope. That is the strength of the signal is a function of time, and we're going to measure the speed of sound. And I'll talk about how we're going to do that in the next video. I need to stop this one at this point. I just wanted to introduce you to this software.